Okay, shall we rock and roll? So, don't worry, almost done. Round 3 of celestial holography. So, last time we saw that working with this conformal primary basis that we've defined, we could see some sort of correspondence between limits of momentum space amplitudes and some sort of CFT data on the celestial sphere. Now, this might sound like a very bold statement, but if you remember what we actually did yesterday, all we were doing was looking at collinear limits, in particular holomorphic collinear limits of, say, graviton scattering amplitudes, and like Mellin transforming these things and seeing that they had the structure of some kind of holomorphic OPE data in a two-dimensional CFT. And these sorts of limits always had, we were always looking at, just very schematically, some limit of one of these celestial amplitudes, and this always went to some kind of interesting CFT data E thing, like an OPE coefficient, times another one of these celestial amplitudes with like some fewer external states. But so far, I've not really told you anything about what these celestial amplitudes themselves, for if you like general kinematics, general quantum numbers, what they actually look like, okay? So the analogy I'd like us all to kind of have in the back of our minds today is just think about momentum space and all the physics that's encoded in the analytic structure of a scattering amplitude in momentum space. Poles, branch cuts, these things tell us physical things that are going on inside of the scattering amplitude, like factorization channels, thresholds, resonances, things like this. So the analytic structure of a scattering amplitude in momentum space is super important. And the question is, what is the analytic structure of a scattering amplitude evaluated in this conformal primary basis? Okay? So in some sense, that's the story we're going to be talking about today. So the setting, we're going to try to make this as simple as possible for today. We're just going to be considering 2-to-2 scattering of massless scalars. If we can't say something about the analytic structure of celestial amplitudes for this, we're hosed, right? Surely we should be able to say something about this. So the setup in momentum space is this. We have some incoming massless momenta, P1 and P2, and some outgoing massless momenta, I'll call them P1 prime, P2 prime, but you can think of this as P3, P4, if you like. And then there's some amplitude that tells us how this scattering process happens. Okay. And for now, I'm going to be completely agnostic about what theory this is, whether this is computed perturbatively or non-perturbatively. Just going to be talking about kinematic statements for the time being. So define the usual Mandelstam invariants. These are the kinematic invariants for this scattering process. They have kind of canonical names, S, T, and U. So for us, S is going to be P1 plus P2 squared. T is going to be P1 minus P1 prime squared. And U is going to be P1 minus P2 prime squared. Okay, and of course, because all these momenta are massless for us, these things are all just dot products, right? So this is just 2 P1 dot P2. This is just minus 2 p1 dot p1 prime. This is minus 2 p1 dot p2 prime. Okay. And thanks to momentum conservation, that implies that their sum s plus t plus u is 0. Okay. So this amplitude in momentum space can always be written as M4, P1, P2, P1 prime, P2 prime, in terms of some distributional piece, which is just given by momentum conservation. P1 plus P2 minus P1 prime minus P2 prime times some interesting piece, M, which is a function of the kinematic invariance, right? S, T, and U. But on the support of that delta function, we don't need all three of them because of that linear relation, right? So we can just think of this thing as a function of S and T. Okay? So this is just momentum conservation. And this is what I would call the interesting part of the amplitude. Okay, now hopefully we're all situation aware enough to know that this is not complexified Minkowski space for the purposes of this lecture. Okay. This is the interesting part of our 4-point scattering amplitude. So if we want to define the celestial amplitude associated to this guy, the prescription is that we just Mellin transform in all 4 of the frequencies of the particles in the game here, right? So this is just equal to integral 0 to infinity. Product I goes from 1 to 4, if you like. D omega I, delta I minus 1. So here, I equals 3 and 4. These are the 2 outgoing guys. I have my delta function. Sorry, let me be consistent with signs everywhere. Incoming guys have a minus. And just rewriting things slightly. Okay. So of course, the omegas and z's are appearing in here as well, right? They're entering in the definition of the Mandelstam invariance. Okay, but I've just written explicitly what the kind of overall momentum conserving delta function is giving us in terms of these omegas and z's. So the question is, without knowing anything about this function, the interesting part of the amplitude, the question is, can we do any of these Mellin integrals kind of against the delta functions that are in the game? And the answer is yes. So to do this, we have to come up with some interesting changes of variables for the Mellin integrals. Okay, so we're going to introduce a new variable, omega, that doesn't have a particle label on it. We're going to say that omega squared is equal to the Mandelstam S. Okay? And then we're going to define omega I hat to be the frequency of the ith particle divided by the omega here, so divided by square root of S, for I equals 2, 3, and 4. Okay? And then it's going to be useful to define a quantity, which I'll call Z, which is just a conformally invariant cross ratio. Z13, Z24 over Z12, Z34, where remember Zij is Zi minus Zj, which is equal to angle bracket Zi, Zj, close angle bracket, right? So this is built out of holomorphic ratios of holomorphic separations on the sphere, and importantly, it's SL2 invariant, right? So because I could build this thing out of angle brackets, okay, that means I've built it out of SL2 invariant objects, and furthermore, it's projectively invariant, right? Because I have one Z1 upstairs, one Z1 downstairs, one Z2 upstairs, one Z2 downstairs, so on and so forth. So this is up to writing 1 over Z. This is the unique conformally invariant cross ratio on the sphere that we can build out of the locations on the sphere associated with our 4 momenta in the scattering process. Okay, so then there's a lemma, which I'm stating as a lemma to give myself the excuse to not prove it for you. This is some, I hesitate to call it interesting, an exercise. The delta function that we have in the scattering amplitude can be rearranged in terms of these variables. So let me just write it, and then I'll describe what's actually happened here. Okay, so we started out life with 4 delta functions. We'd better wind up with 4 delta functions here. 1, 2, 3, 4, okay? And then proving this lemma is just an exercise in keeping track of Jacobian factors as you shuffle stuff in and out. Okay, it's, yes?
When they say name, you change your variables?
Why have I done this change of variables? Because I want to find a way to do as many of these Mellin integrals against delta functions. So I didn't come up with this change of variables, and I'm going to struggle to tell you what the intuition behind it is, other than experimenting with good ways to do this. Yeah, I mean, I guess what you know is that for a 4-point, okay, let me try to construct some intuition for you. What you know is that for this 4-point scattering amplitude, somehow really there's only one energy scale in the game, which is like center of mass energy. So in the T channel, that would be the Mandelstam invariant S. So you might say it makes sense to try and identify one sort of scale, energy scale, that you'd like to be left over at the end of the day that you can't integrate away against the delta function. So that would motivate this change of variables. And then the idea is that you just are defining some dimensionless quantities, omega hat I, once you've identified that universal scale. If you're asking me, would I have thought of doing this? The answer is probably no. But this rewriting has appeared, I should give the people who did think of it credit. So this rewriting has appeared in a variety of papers. I think the first one is by Stieberger and Taylor, maybe from 2017. Don't quote me on that. And they may have deduced bits of this change of variables just from kind of general physical considerations. So you see, one of the delta functions sets the conformally invariant cross ratio to be real. And there's kind of a general argument, which I will fail to reproduce now, that if you have a 4-point scattering process that's constrained by momentum conservation, if you look at the kind of angular bits of all those, they have to lie on an equator of a sphere. They can't be in generic positions on the celestial sphere. And this delta function is precisely the thing that's forcing them to lie on an equator. So you can kind of guess that this delta function has to be there, and then you can start guessing other bits of the formula using Lorentz invariance and dimensional analysis.
Is this how related to like if you would take like a plane jewel and you would construct like a twisted polygon and get it into like these
Yeah. So yeah, very good. So if you have that Kool-Aid that you've drank, then there is some intuition behind this. So there's Stieberger, Taylor. Then there was a paper by Arkani Hamed, Pate, Reclariu, and Strominger that does this a bit more explicitly. And again, they give some kind of vague, well, maybe vague is not fair. They give some physical intuition, maybe more along the lines of what Jeffrey suggested about why this delta function should be there, and then they just work through manipulating the four momentum conserving delta functions to break them apart in this way. But yeah, perhaps I'm just, like, to me it's not obvious, like when I wake up in the morning, that this is what I should do. But I think the vague motivation is pulling out some universal center of mass scale that you expect to be left over at the end of the day, and then just finding a way to hammer everything. But now you can see that this is sort of going to do what we want, right? Because if we change variables in the integration measure here, we're going to be able to do all the omega hat integrals just against these delta functions. But we're not going to be able to do the omega integral. So the center of mass scale will be left over at the end of the day, which is sort of what we were shooting for. So under the change of variables from, say, omega 1, omega 2, omega 3, omega 4, to omega hat 2, omega hat 3, omega hat 4, you can show the integral measure. So we have 4 of these kind of d-log type measures in the energies or in the frequencies. This becomes 2 times a bunch of integrals still from 0 to infinity of d omega over omega, d omega hat 2. Well, let me write it this way. Prod I goes from 2 to 4, d omega hat I, omega hat I. So the measure pretty much stays the same. We kick out this factor of 2, which isn't surprising because S went like omega squared. Okay. So
Sorry, is this measure embedded in the standard transformation?
It's invariant under scale transformations of the energies. Yeah, I mean it's just a scalar. Yeah, it's just a bunch of d logs. So that's I think all you can say about it.
Not like Lorentz invariant or whatever.
Well, I mean these energies are Lorentz invariants, I guess. So somehow by construction the thing is. I don't think there's much more to say about. Of course, this isn't the only omega dependence in the integral, right? We still have all of the omegas, or omegas and omega hats in here, and everything going on in this guy, which we're being agnostic about for the time being. Okay, so on the support of the delta functions that we have after changing variables, the Mandelstam invariant T, so this is minus 2 omega 1 omega 3 mod Z13 squared. Okay, so this it's a bit of algebra. This is, you can show, so all you need to use here are the three delta functions, well, these two delta functions at the bottom, and the definition of omega and omega hat. This thing is omega minus omega squared square root mod Z 2, 4 squared mod Z 1, 3, oh sorry, to the fourth over Z squared Z 1, 2 to the fourth. So you start generating a bunch of square roots when you use these delta functions, but then the thing inside the square root is a perfect square. And furthermore, you see that you need to remember the definition of this conformally invariant cross ratio, and you see that you're going to cancel some powers of this. So this is just equal to minus omega squared Z bar, where Z is the complex conjugate of our conformally invariant cross ratio, but we know that that's real. So this is just minus omega squared Z. Okay. So the upshot of this is that we now know also what the functional dependence of the interesting part of the amplitude is in terms of the new variables that we've defined, right? So what this means is that we obtain a new expression for the celestial amplitude, which is just going to be equal to a half and a bunch of Mellin integrals, d omega over omega, product I goes from 2 to 4, d omega hat I over omega hat I, and then, sorry, we can just, I'm not going to bother writing this. We can just do all these integrals against the delta functions now. And what one is left with is some gnarly looking thing. Let's write it this way. D omega, omega to the beta minus 1 times 2, something that actually comes right out of the integral. There's no omega dependence in it. Okay, so what we're left with after we do this change of variables and do as many of the integrals against the delta functions as we can is the following. We have one Mellin integral left, which is over, if you like, the center of mass energy of the scattering process, where this beta, this is just the sum, I goes from 1 to 4 of delta I minus 1. Okay. Then we have this ugly mess in square brackets, but notice there's no omega dependence in here. So this just comes outside of the integral. And all the theory-dependent information, all the interesting bit of the scattering amplitude is just left in integrating the kind of interesting bit of the momentum space scattering amplitude, where you set the Mandelstam S equal to omega squared, and the Mandelstam T equal to minus Z omega squared. Okay? So if someone hands you a momentum space amplitude, you know exactly what Mellin integral you have to do to compute the celestial amplitude. So typically what we do is we write the 4-point celestial amplitude, which again is a function of these conformal dimensions, these z's, for each of the 4 external particles. We write it as some x times something we call a, function of beta, this sum, so if you like, weighted sum of the conformal dimensions, and z, which is this conformal cross ratio. You should think of z as encoding the scattering angle. Okay? Where x is this universal theory-independent prefactor that we wrote up there. It has this delta function that makes the conformal cross ratio real. And then these factors that depend on the conformal cross ratios and the separations between the points on the celestial sphere. And their conformal dimensions. And then the interesting part of the celestial amplitude, which only depends, it doesn't depend on the conformal dimensions independently, it just depends on the sum of them, beta, and on the scattering angle, this thing is the interesting integral that we have left over. Okay? So there's a few things we learned just from this. I emphasize this has been a completely kinematical exercise. We've made no assumptions whatsoever about what theory is governing our 4-point scattering process, or what order this thing has been computed to in perturbation theory. If it's been computed in perturbation theory at all, maybe it's computed non-perturbatively somehow. So the first thing is something I've been alluding to on and off throughout these lectures, which is if you look at this universal prefactor, this thing we're calling x, there's a delta function in it, in the conformally invariant cross ratio. This means that if you like the 4-point correlator on the celestial sphere, if there is some 2D CFT computing these things, the 4-point correlators are distributional, right? So that's not something you can encounter in local unitary CFTs in 2 dimensions. So this is the alarm bell that if there is a dynamical 2D CFT producing these celestial amplitudes, it can't be a garden variety one, because it has this distributional nature built into it, which is built into it regardless of what scattering process we're actually considering, because it's in this universal prefactor. Okay? Yeah?
Could not these universal factors due to the symmetries of the inner states? Because the Klein-Gordon has an infinite dimensional symmetry, has a BMS symmetry. And, at the end, you are telling some general.
I mean, I think.
Entering the dynamics.
Yeah, I mean, I think it is due to a symmetry, but that symmetry is just translation invariance. This is just the remaining echo of momentum conservation.
What I'm saying is that free Klein-Gordon field has a BMS symmetry.
But
Therefore,
this delta function will be here for any massless scattering process. I've written this for scalars, but you could do this for massless fields of any spin. This delta function is here. But this is.
Going to asymptotics, we'll have BMS symmetry.
But this isn't a consequence of BMS symmetry. This is a consequence of translation invariance.
Okay, I should believe you because I don't have.
I mean, this is literally a momentum conserving delta function. This is the one bit of, so we had 4 momentum conserving delta functions. We broke them apart in some super non-obvious way. I mean, this is literally a momentum conserving delta function. The integral hasn't done anything to this. So you should really view this as a piece of momentum conservation. It doesn't have anything to do with, furthermore, if you were considering massive scattering amplitudes, this would still be here. It's just translation invariance. It's nothing more sophisticated than this. And like I say, I've written this for scalar scattering, but if you wrote it for any spin, the only thing that would change are these exponents here and here. This delta function doesn't change, this exponent doesn't change, and this integral doesn't change. Yeah, there was a question.
If that delta is due to momentum conservation, then why is it so strange then?
It's not strange from a momentum conservation point of view. It's strange from a 2D CFT point of view, right? So again, I'll keep reiterating this fact because I think it's an important one. This whole celestial holography story is a two-way street. Either you can think of it as a way to just rewrite scattering amplitudes in a way where we have some CFT tools at our disposal, in which case this is completely unsurprising. Yeah, I mean, the scattering amplitude started out with some delta functions in it in momentum space. Why shouldn't it have some delta functions in it once I change variables to this kind of celestial parameterization, right? But if you take the other street, that there should be some 2D CFT that lives on the sphere that computes dynamically scattering amplitudes for us, which is a much cooler, much more ambitious perspective, then what this is saying is that that CFT cannot be a local unitary one, which means that, like I say, everything in the big yellow book somehow stops helping you. So I agree, there's a way of looking at this where this is just completely unsurprising, but if you were hoping to kind of implement some sort of bootstrap program for these things, this is already a problem, the fact that the 4-point correlators are distributional. Now, later in the week, Yannick, who lurks above us, so to speak, is gonna tell us about Carolian stuff, and in the Carolian world, there may be some way to kind of, make the things look less distributional than this. Whether Yannick will say anything about this, I don't want to put him on. He's shaking his head. So, okay. But, yeah. Okay? So if we want to compute explicitly one of these celestial amplitudes, all we have to do is compute one Mellin integral at 4 points. You take your favorite 4-point momentum space scattering amplitude, you set the Mandelstam variables s equal to omega squared, t equal to minus z omega squared, and then you do a Mellin integral in the COM energy scale omega. Okay? So let's see what that does.
You said that if you had spinning particles, then that part would be the same for the exponents there. But it's just on the CIJ. So can I think of like, is it the twist instead of the spinning dimension?
Yeah. So this is the bit that would, detect the spin of the operator or the twist of the operator. Yeah. And this bit is the, this bit is the kind of twist-independent bit of the conformal block or something. So So yeah, the point is you never get away from doing this integral. And this universal prefactor is something that once you've gone through this horrible kind of reshuffling of delta functions calculation once, you don't have to think about it again. You just write down the prefactor every time without having to do a calculation.
And can I write it now with the crossing symmetries getting cross ratios?
Yeah, so that's right. So crossing means that the thing should be invariant under switching these arguments.
It will be like something not one minus
It's not Z. Let's see. So no, we'd need to be a little careful. So we'd want to send Z. We'd have to probably scale omega as well to get a Z to pop out here. Yeah, yeah. So what you might end up doing is kicking out some powers of Z in the measure. It's okay, this thing's still a function of Z. Just bring them outside of the integral. Okay, so let's see what happens for the simplest example we could think of. Let's consider gravitational scattering of scalars. And we'll even just focus on a single channel. Right, so this is this Feynman diagram. Okay. So this is a tree level. So the idea is we're going to compute a tree level celestial amplitude of gravitational scattering of two massless scalars in one kinematic channel. Okay. And I mean, you can all amuse yourself by doing this, this computation, and what you find is that M4 is delta 4 with, let's call this M tree S T, where this M tree, this is like G over T S squared plus TS. Okay? For minimally coupled scalars to gravity. Okay. There's maybe some number in front of this that I'm not being careful about, but who cares? Okay. So what that means is that M tree evaluated on S equals omega squared, T equals minus Z omega squared. This is equal to minus G omega squared 1 minus Z over Z. Now remember, Z is our conformally invariant cross ratio. So then the interesting bit of the celestial amplitude, let's call it A tree of beta and Z. This is minus G 1 minus Z over Z, integral 0 to infinity d omega, omega to the beta plus 1. And if I let x be log omega, I can rewrite this integral in a sort of more illuminating way, perhaps. Like this. This is not a convergent integral, right? So unless beta plus 2 is imaginary, this integral is exponentially divergent. Right, so if, in this case, right, you would get a delta function. Okay, but there's nothing physical about beta taking this value. Right? It has nothing to do with the principal continuous series or anything. For generic choices of the conformal dimensions, this thing is not defined. So the celestial amplitude doesn't exist. Okay? Or at least it doesn't exist even as a distribution on a Schwartz space of functions. Okay, so you might, and I should emphasize furthermore, even in this case, if you said, well, okay, there's just some rule telling me what the allowed conformal dimensions are for 4-point scattering, even in this case, I get something distributional. So it's not analytic. It's not like a meromorphic function on the complex beta plane. You know, from a momentum space perspective, you would have said that all the distributionality you'd like to allow in these things is already in this universal prefactor x, and you'd want this curly a, the interesting bit of the amplitude, to be at least in some local bit of the complex beta plane an analytic function. And this is just never true. Okay. So, on the one hand, this might seem surprising. On the other hand, it's not really surprising at all. Gravity, general relativity, famously not a UV-complete quantum field theory. And even though the tree-level amplitudes, yes?
In that integral up there, why do you have beta plus 1 instead of beta minus 1?
Because m tree went like omega squared. Yeah. So, you know, GR, famously not a UV-complete theory of quantum gravity. You see this even with tree-level scattering amplitudes in momentum space that are completely well-defined. This thing in the high energy limit, right, this thing's going like s squared over t, so it's blowing up, right? And this Mellon integral is sweeping out the whole center of mass energy scale from 0 to infinity. So even though we've only done a tree-level computation, which in momentum space was completely civilized, the Mellon integral knows that it came from a UV incomplete theory. Okay. So you might think, well, okay, maybe if I add some loops into the game, I can start trying to tame this. So working to any finite order in perturbation theory, so let's say we're going to sum contributions up to big L loops of our 4-point amplitude. You can show that this is always going to be given by some finite sum. So here these indices n and m run from 0 to some finite natural number of terms that are like omega to the m log omega to the n. Okay? So then that means that one would be dealing with Mellin integrals of the form d omega, omega to the beta plus 1 plus m, log omega to the n, and these are integrals of the form x to the n e to the beta plus 2 plus m x, and these are still never analytic, right? So these things are, again, undefined for all beta in the complex plane, except when beta plus 2 plus m is pure imaginary, in which case you'll get an n times differentiated delta function, right? So it's still not analytic, right? So the upshot here is that perturbative celestial amplitudes, they don't exist as, let me say quasi-analytic functions in the space of conformal dimensions. Okay? So what the heck has this field been doing for the last 10 years? Well, in some sense, we've already answered this question. There are universal pieces of scattering amplitudes, like soft factors or collinear splitting functions, that do behave well under Mellin transform, and we can read off some interesting things, like these celestial OPE coefficients. But somehow, the hard bit of the celestial amplitude is not something that you can generically make sense of in perturbation theory. Now, I used the example of gravitational scattering here because I think it's a particularly nice one, but you could imagine, suppose I just had a cubic scalar or something, cubic massless scalar. You might say, well, that's gonna be okay. Well, then it's actually the small omega bit of the amplitude that's gonna screw you up, okay? And you could do gauge theory, right? So if I was exchanging a photon or something, this is classically scale invariant in 4 dimensions. So actually something nice will happen there, but the amplitude still won't be an analytic function. It'll just be a delta function in beta, essentially, okay? So this is a very generic feature of celestial amplitudes. And the question is there any sense in which we can cure it? So I was talking to some of you about this the other day. Imagine trying to set up ADS CFT, but where all of the CFT correlation functions you had were not well defined. You have nothing to match onto, right? So here we're in a similar situation where we want to try and set up some sort of holographic duality, but we don't actually have any correlators that we can match, right? For me, this seems like a big problem and one that's worth thinking about how to get around. And that's what I'd like to talk about for whatever, the last half hour or so. Is that okay? But are there any questions about this sort of generic fact? Mm-hmm. Yeah, so I completely agree. I mean, I think one could, so Yannick, stop me if I start answering a question that you feel isn't the one you've asked. So one, even before thinking about IR divergences, you could just think in momentum space, the amplitude is also not an analytic function. It has a huge delta function that sits out in front of it. But the point is that we can strip off this kind of non-analytic piece. It's something universal, theory independent, and it doesn't really depend on any of the quantum numbers of the scattering process other than the momenta. It doesn't see helicities, charges, anything like that. It just comes out. And then the thing that's left over, the blackboard bold M, depends on all of the quantum numbers in the scattering process. So you could try to do something similar here, where you say, well, okay, these exponential integrals are not well defined, but just like I would do with momentum space scattering amplitudes, I want to pair these things with some wave packet. And that wave packet in momentum space is the thing that eats the distributional part of the amplitude. So we have wave packets that live in Schwartz space. What is Schwartz space? Some functional space where the function and all of its derivatives die off sufficiently quickly at large distances. And so the delta function is a distribution on that space. Fine, and the interesting part of the amplitude still contains all the kind of physical information of the scattering process. Here, and there have been papers written about this, what sort of function space of wave packets you could pair integrals like this with to get numbers. And they exist mathematically. But then the problem is the bit of the amplitude that you have to strip off to define the distributional part of the amplitude takes all of the beta dependence with it. So the finite bit of the amplitude only knows about the scattering angle. You lose the dependence on a whole important set of quantum numbers in the theory. So even though on some mathematical level this is a resolution of the problem, for me I'm not convinced it's a physically satisfactory resolution because the thing you're left over with, the analytic function, doesn't have any beta dependence. So you lose all the kind of rich analyticity that you would have had in momentum space. So with IR divergences, I think you would typically say something similar, that these things factorize, and there's some universal part of the amplitude that doesn't see them and contains analytic structure that still encodes, you know, for particle production or something, the sort of thing that you would test at a particle collider. Yeah?
What we seem to have done here is taken variables that behave nicely under translations to variables that are nice as to objects. So are you making the statement that S matrix is not a thing that likes to deal with variables describing SLUC?
No, that's not what I'm saying. What I'm saying is that perturbation theory with a dimensionful coupling constant doesn't play well with an integral that sweeps out all the dimensionful scales of the theory. Yeah, so it's a good question, but my claim is that this has less to do with manifesting boost invariance and more to do with the fact that you've swept out all the energy scales in the theory. Yeah. So let me try to be maybe a bit more explicit about this. So in some sense, this is not really surprising. The Mellon transform sweeps out the entire energy scale from the IR all the way up to the UV. And that means you cannot work with low energy effective amplitudes. What do I mean by low energy effective amplitudes? I mean amplitudes from a low energy effective field theory, like GR, right? Yeah. Yeah, so it is better in the sense that what you will, kind of generically get for these Mellin integrals are delta functions or derivatives of delta functions. So it's better in the sense that the amplitude has a definition as a distribution on a reasonable function space. But my claim is that we don't want there to be any distributional aspect of this bit of the amplitude. All the distributional bits should be in the thing we called x earlier. So it is better, and that's a consequence of the scale invariance. Sorry, say that again? Yeah. Yeah, absolutely. So like I say, one thing people often do in the literature on this topic is work with, say, gluon scattering amplitudes in 4D, where just like with, say, phi to the fourth, it's classically conformally invariant. And then they have these delta functions in beta that appear everywhere. And okay, you have some explicit expression you can work with that looks kind of civilized, but the thing that multiplies the delta function in beta sort of doesn't have any beta dependence. So the analytic part of the amplitude isn't going to tell you anything about interesting stuff that happens in the complex beta plane. Instead, you just have 0, 0, 0, 0, 0, 0. So it is better, but I claim it's not better in the way you might have hoped. So again, just to maybe reiterate this point, in momentum space, we have a distributional part of the amplitude, the momentum conserving delta function, and then we have the kinematical part of the amplitude, which is not distributional, depends on all of the quantum numbers of the scattering process, and is an analytic function in some region of the space of kinematic invariance, right? So the natural thing to hope for here is that you also have a distributional part of the celestial amplitude, this thing x, and then you have an interesting part of the celestial amplitude, which depends on all of the quantum numbers, beta and z, and should be, at least in some region of the complex beta plane, an analytic function. And we don't have this for any theory to finite order in perturbation theory.
Why do you want to treat the betas as quantum numbers? Because you don't really have them in the arbitrary itself.
Yeah, you do. They're playing the role of energy.
Oh, sure.
Yeah. Mm-hmm. Yeah, they're absolutely quantum numbers. So if I lose all the beta dependence in the distributional part of the amplitude, I claim that it's like saying you only know about angles and not energy scales. And for a conformally invariant theory, that would be something that would make sense. But for a theory coupled to gravity, for instance, certainly doesn't make sense.
Can I fix some of the structure with celestial amplitude using the estimated structure?
It's a good question. I don't know the answer. Yeah, I don't know the answer.
And what about if I, for example, solve the hydrogen atom and like construct the full S vectors, the liquid trigger equation? If I now put it in this Mellin integral, what's happening there?
Yeah, good. Okay, so let me tell you what I'm going to tell you next, and I think this will be like what you're describing. So so the upshot of this upshot is that if I'm doing things to finite order in perturbation theory, I should expect to get broken answers. So then the kind of converse of that statement is that what I should do is not work to finite order in perturbation theory, but solve some problem exactly to all orders. That's hard, right? So the question is there some regime, for instance, in this toy example we're talking about of 2-to-2 massless scalar scattering mediated by gravity, is there some regime of that scattering amplitude that is solvable to all orders in perturbation theory? And the answer is yes. Okay. So later this week, so I'm going to give you some really basic, sketchy introduction to these ideas, but later this week you guys are going to have Carlo Heisenberg telling you about this stuff, and this guy is like the god of this subject, so you should ask him loads of questions. I'm just going to give you some very sketchy overview of the subject. Okay, so the basic idea is we want to find some regime where the perturbative series in G Newton, can be resummed. And the regime we'll be interested in is what's called the iconal regime. Okay, so what is this? So for quantum field theory coupled to gravity, this iconal approximation of 2-to-2 scattering holds when your Mandelstam variable S is much larger than minus t, or the absolute value of t, and G Newton times S is much, much bigger than h bar. So what do these things mean? This means that you have small scattering angle. And this means that you have, it's often called the trans-Planckian energy condition. The center of mass energy of the scattering process is very, very large, but it's also some kind of classicality condition. So this iconal regime is accessing the small angle kind of classical regime of 2-to-2 scattering. And if two interesting things happen in these limits, then something miraculous happens with the scattering amplitude. Well, miraculous is maybe an overstatement. Something awesome happens with the scattering amplitude. So if, first of all, the small scattering angle regime isolates ladder and cross-ladder diagrams at all loops in perturbation theory. So what do I mean by ladder and cross-ladder diagrams? I mean diagrams like this. Right? And what do I mean by isolate? I mean all the other diagrams at that same loop order in perturbation theory are subleading in T over S. Okay. So if that is true, and the series can be resummed in a way that I'm going to be kind of deliberately vague about. It can't be resummed in momentum space, but rather if you Fourier transform it to what's called impact parameter space, then, so this is in the classical limit, then something interesting happens. And let me just first of all say that not every theory has these properties when you look at the iconal approximation. So if you consider cubic scalar theory, it's not the case that in the small angle scattering limit, these diagrams dominate to all orders in perturbation theory. Something weird happens at 3 loops, and other diagrams sneak in that are over-dominant in T over S that beat these. It's not always the case that even if these diagrams dominate, you can resum them. Think about non-abelian gauge theory. So let's have some quarks exchanging gluons, right? The box and cross box diagrams come with different color factors. So you can't sum them together, right? So not every theory has these features. But if you can establish that your theory passes these 2 litmus tests, then something called iconal exponentiation holds. So what is that? It means that, put a factor of I here to get things right. The iconal limit, so small scattering classical limit of my 4-point scattering amplitude momentum space, this is equal to an iconal amplitude, which is equal to 2s integral over a 2-dimensional transverse plane times an exponent of I delta 0 x perp minus I q perp x perp, where this delta 0 of x perp, this is just the Fourier transform of what we call the Born approximation. That's just the single exchange tree level diagram evaluated in this limit, small scattering angle classical. And q perp, this is just the exchange momentum. So q perp squared is minus t. Okay. So what is this actually saying? It's saying that in this limit, if these properties hold, the amplitude is really entirely controlled by the single exchange. So that is the ladder and cross ladder diagrams are just repeated iterations of single graviton exchange. Okay. You can resum the perturbation series as an exponential. Okay. And it's also the case that for the process we're interested in, of 2-to-2 scattering of massless scalars mediated by graviton exchange, not only do A and B hold, so we have a formula like this, but you can also do this x perp integral and get what I think is one of the great amplitude formulae in physics. Sorry, say that again? Ah, yeah, sorry. It's the single exchange, tree level. And we assume here that we've evaluated this in the small angle classical limit. So for instance, before when we wrote M tree, right, there was S squared over T, but then there was also a kind of S term, because it was, the numerator was S squared plus T times S. That last term we can neglect in this small scattering approximation because it's subleading in T over S. Okay? So for 2-to-2 massless scalar gravitational scattering, there's an awesome formula for this iconal amplitude, which is just try to get all the factors right here. Okay, so what's going on here? This is the Born amplitude. And everything else is a phase. there's this quantity mu. This is an IR regulator. We're in 4 dimensions. We're considering massless exchanges. The box diagram has IR divergences. So we introduce an arbitrary mass scale, mu, to regularize those divergences. It's arbitrary because it drops out of cross sections, right? Because this is a phase. So in the iconal approximation, the cross section is just the tree level cross section. Okay, so the idea is now, rather than just using the Born term, or some finite number of ladders or cross ladders, which we've seen lead to exponentially divergent celestial amplitudes, the idea is to Mellin transform that whole thing. And you might say, well, it only differs from the tree level thing by a phase, but at large energies, that phase is rapidly oscillating. And it could tame the Mellin integral. So we can now consider what we'll call A iconal, beta and z. This is minus g over z, integral 0 to infinity, d omega, omega, beta plus 1, gamma minus I g omega squared, gamma I g omega squared, 4 mu squared omega squared z minus I g omega squared. Okay? So even before we look to see if this is an integral that converges to something sensible, there's something cool you can notice here, which is a tip-off that we're on to a good idea, which is that I can just rescale omega and factor out all of the g Newton dependence of the amplitude in one go. Okay? So this is just equal to minus 1 over 2 g to the beta over 2 z integral 0 to infinity d omega omega to beta over 2 gamma minus I omega gamma I omega for mu twiddle squared for omega z minus I omega 4. So mu twiddle is now again just an arbitrary scale where we've absorbed some powers of g. Okay, so this thing is now strongly non-perturbative in g Newton, right? Beta is some complex number, right? And that's the whole point. After we do the Mellin transform, our notion of perturbation series in g Newton is meaningless. G Newton had mass dimension, so it's like an energy scale, but we've integrated out all the energy scales in the theory. Okay, so So what you could wonder or worry is that this still isn't going to make sense because maybe the range of Mellin integration takes us outside the regime of validity of the iconal approximation. Remember, that amplitude that we're integrating is supposed to hold for small scattering angle and very high center of mass energies. Okay? So could worry. that the Mellin integral takes us outside of the iconal regime. So there's two ways. So the first answer is just to tell you in advance, that's not actually going to be a problem. But even if it was, there's some sense in which you might not want to lose too much sleep about it at this stage, because what you have is some explicit formula that depends on the kinematic invariance, and you're just going to Mellin transform it and see, do you get something civilized? And if you do, then you're happy, right? And you can worry about what the regime of validity of that formula is after the fact. But in point of fact, the small angle constraint, this just boils down to saying that the conformal cross ratio is very small, much smaller than 1. That's fine. The integral, Mellin integral doesn't touch the conformal cross ratio. So we can just say that Z is very small here. Doesn't matter. Okay? And then classicality, this is saying that G over H bar omega squared needs to be much greater than 1. And clearly, there is a small omega regime of that integral which violates this constraint. So this constraint is clearly violated. So this one is okay, no problem. We just impose that by hand by tuning Z. This one is clearly violated by the small omega region of integration. Okay? But actually, this also isn't something to lose too much sleep about, because the region of the Mellin integral that gave us trouble to any finite order in perturbation series was the large omega regime. Right? So this classicality constraint doesn't really have anything to do with the problems we were having defining the Mellin integrals before. All it means is that if we can show that this Mellin integral converges to some sort of analytic function, any properties of that analytic function that are due to the small omega region of integration are liable to receive quantum corrections. That's all it means. So features so if this thing exists, which we haven't shown yet, but if it does, any of its features which come from the kind of small omega part of the integral, they could receive quantum corrections. Okay. But that's not something we should be losing too much sleep over, the same way that when we compute a tree level or an L-loop scattering amplitude in our favorite effective field theory and momentum space, that amplitude is liable to receive corrections from higher loop effects, from quantum effects. Okie doke. So, we know that the potentially problematic region of integration in that celestial amplitude we're trying to define is the large omega regime. So problems with the existence of this iconal celestial amplitude could arise from large omega. So it suffices to consider some large omega approximation of this integral to establish whether it converges or not. So use Stirling approximation on the gamma functions, and you'll find that this ratio minus I omega gamma I omega, this is equal to I E to the 2I omega, omega to the minus 2I omega 1 order 1 over omega. So this is just a consequence of Stirling's approximation for the gamma function. So that means that the fate of this iconal celestial amplitude is tied to the convergence or not of integrals of the integral 0 to infinity d omega, omega to the beta over 2, omega to the minus I omega x I omega 2 plus log z over 4 mu to the squared. Okay, so this is just, if you like, the large omega approximation of the integrand there. Okay? So we want to establish, does this integral converge? Okay. Lemma. Let's let A and B be any two complex numbers, and C be a positive real number. Then any integral of the form that's right, 0 to infinity d omega, omega to the a minus 1, e to the I b omega, omega to the minus I c omega is a meromorphic function of A. Okay, so any integral of that form converges to a meromorphic function of A. This is precisely, our integral is precisely one of this family, right? So A minus 1 is beta over 2, right? C, in our case, is 1. That's a positive real number. And B is this big mess, okay? So how do you prove this? You just, you consider the contour in the lower right complex plane. You have some contour C1, which is, this is the interesting bit of the integral you're trying to compute. Then there's some bit at infinity, and then some bit coming up the negative imaginary axis. For c greater than 0, the integral along this contour at infinity is exponentially damped. So you can throw it away. So then by Cauchy's theorem, we have that the integral we're interested in, d omega, omega to the a minus 1, e to the I b omega, omega to the minus I c omega. This is equal to minus I to the a, integral 0 to infinity, d omega, omega to the a minus 1, exp B plus pi over 2c omega minus c omega, which is analytic in A apart from isolated poles arising from the small omega region of integration. Okay, so what we've proven is that this integral converges to a meromorphic function in A. And this is exactly what we wanted, right? A is playing the role of beta in this kind of general family of integrals. So the upshot is that this iconal celestial amplitude exists as a meromorphic function of beta. The poles it has in beta are located at integers on the negative real axis, just like our conformally soft wave functions were located at conformal dimension integers on the negative real axis. And you can characterize what the structure of these poles is, what their residues are, but these are all liable to receive quantum correction, so you shouldn't view them as being something too universal. If what we don't have is an explicit formula for this thing, for generic beta. However, if you impose the strict iconal approximation, that is to say, the classicality constraint, which we know is violated by the small omega regime, that's the same as taking a large real part of beta, then the Mellin integral is dominated by a saddle point at very large omega, right? So for large enough beta, you'll be dominated by a saddle that's consistent with the classicality constraint. And your saddle at very large omega gives a more explicit answer. Let me ignore overall factors. Okay, so in some sense, this really is what you should consider the iconal celestial amplitude, because it's a thing that's consistent with both the limits that define the iconal regime. Okay. So, I mean, we're out of time. So let me just conclude with some sort of vague general thoughts here. So there's one other example that we know of where we can get kind of explicit sort of meromorphic celestial amplitudes, and that's in string theory. So if you consider a string amplitude on some finite genus Riemann surface, you might say, well, okay, that's finite order in G newtons, so aren't I going to have the same problem? But it's actually all orders in alpha prime, right? So alpha prime there, the perturbation series in the 2D CFT, you can resum, and then the Kobe-Nielsen factors you get in your string amplitude are the things that are playing the role of the iconal phase here. So we have someone in the audience, Xavier, who's an expert on this stuff. But I think that finding more examples where we have some kind of resummation that leads to well-defined celestial amplitudes is an important open problem for this field. Because again, just imagine you were trying to do ADS-CFT, but you didn't have any explicit correlation functions to work with. It would be hopeless, right? This is the situation we're in with celestial holography. We have lots of nice kind of kinematical structures, but very little concrete dynamical structures that we can hang our hats on, and that's because we just don't have explicit celestial amplitudes to work with. So we can see that in the strict diconal regime, we get something explicit. You can imagine now doing an expansion in T over S, going away from this small scattering angle regime. This is something Carlo is an expert on. And resummations still hold to some orders in this expansion. Do they lead to sensible celestial amplitudes? How far can you go in this expansion before you start seeing the melon transform blow up? And what does it say about the need to have some kind of scale in the game to get well-defined celestial objects more generally? These are questions I don't have the answers to, but I think it would be very interesting for one of you to provide answers. So with that, I'll stop here.